An aircraft does not fly because of its engines. It flies because of the air it pushes downward, and that air has to have weight. But the air over Dubai, in the middle of summer, weighs noticeably less than the air the aircraft was designed and certified in. Hot air expands. The molecules move further apart. A cubic meter of it contains fewer molecules than the same cubic meter would contain on a cool morning, and a wing moving through it at the same speed produces less lift. At first, this might just seem like a scheduling preference, an airline choosing a night departure because passengers sleep better. But the runway is a fixed length. It does not get longer on the hottest day of the year, and the aircraft still has to be off the ground before it ends. So how much weight does a heavy long-haul aircraft have to leave on the ground on a summer afternoon in the Gulf? And what happens to the surface it is rolling on when the pavement itself gets hot enough to move? You have felt the beginning of this without knowing what it was. Sitting in a cabin on a taxiway in the Gulf in August, holding, air conditioning fighting and losing, waiting for a figure the crew are still working on. Then the aircraft lines up, and it uses far more of the runway than you remember it using anywhere else. The acceleration feels flatter and longer, and the nose stays down past the point where you expected it to come up. Nothing about that is a fault. The aircraft is doing exactly what the numbers said it would do. To understand those numbers, you have to stop looking at the aeroplane and start looking at the air it is trying to hold on to. Start with the standard case. Lift is produced by a wing moving through a fluid, and the amount of it depends on the density of that fluid, on the square of the speed, on the area of the wing, and on the angle it meets the air at. Density is not a constant. It falls as temperature rises, and it falls as altitude increases, and those two effects are interchangeable. A hot day at sea level can produce exactly the same air density as a cool day thousands of feet up a mountain. Aviation gives this equivalence a name. The Federal Aviation Administration defines density altitude as pressure altitude corrected for non-standard temperature, and describes it plainly as the altitude the aircraft feels it is at. On a severe summer afternoon in a Gulf city, a runway that sits essentially at sea level can present the aircraft with an aerodynamic environment belonging to somewhere several thousand feet higher. The aircraft does not know it is at sea level. It only knows the air, and that air is doing three separate things to it at once, all in the same direction. The first is the wing. Less dense air means less lift at any given speed, so the aircraft must reach a higher true speed before the wing can carry the weight. Higher speed means a longer acceleration, and a longer acceleration means more runway consumed before the nose can be raised. The second is the engine. A jet engine is an air-breathing machine. It produces thrust by taking in a mass of air, accelerating it and throwing it backwards, and the thrust available depends directly on how much mass it can ingest per second. Thin air means less mass through the same fan, which means less thrust. Modern engines are flat-rated, which means they are certified to deliver a constant maximum thrust up to a certain outside air temperature, deliberately holding back below it to protect the engine and extend its life. Above that temperature, the available thrust begins to fall away. So on the hottest afternoons, the aircraft needs more speed than usual and has less thrust than usual to reach it. There are three of these forces, and the third one is not about the aeroplane at all. This channel exists to take apart the systems that cities and their infrastructure quietly run on, so if that is what you came for, subscribe and stay with it. The third is the ground itself, and this one is slower and less visible, and it is where the story turns from aviation into civil engineering. A runway is not a slab of stone. Most runway surfaces are flexible pavements, built from layers of aggregate topped with asphalt, and asphalt is a composite of stone held together by bitumen. Bitumen is what engineers call a viscoelastic material, which is a formal way of saying that its behavior depends on temperature and on how quickly you load it. When it is cool, it behaves like a solid. When it is hot, it begins to behave very slowly, like an extremely thick liquid. Load a cool asphalt surface, and it springs back. Load a hot asphalt surface repeatedly in the same place, and it does not fully spring back. It deforms permanently, and the deformation accumulates. The design response to this is the choice of binder. Asphalt binders are specified against the temperature range the pavement will actually experience, not the temperature of the air. and pavement surface temperature on a dark surface under a desert sun runs far above the air temperature measured in the shade beside it. A binder chosen for a temperate climate would rut under desert conditions. A binder chosen for extreme heat is stiffer at high temperature by design, and specifying it correctly is the single most important decision in the whole pavement. The load that is being applied to it is not a car. A heavy wide-body aircraft concentrates hundreds of tons onto a small number of tires inflated to very high pressures, and that produces contact stresses far beyond anything a road ever sees. The International Civil Aviation Organization uses a system for describing this, in which the strength of a pavement is published as a numerical classification and each aircraft carries a corresponding number, so operators can determine whether a given aircraft can use a given surface and how often. The system exists precisely because pavement damage is not caused by a single load. It is caused by repetition, and the repetition is not spread evenly. Aircraft do not wander across the width of a runway. They line up on the center line, and their main gear tracks fall within a narrow band each time. Thousands of movements a year concentrate their loading into the same 2 strips of asphalt. Add a surface that is hot enough for the binder to soften, and permanent deformation begins to build along those strips, as shallow ruts and slight shoving at the edges. It is measured in millimeters over years, and it is invisible to a passenger, but it is the reason runway pavements have a service life measured in a decade or so, rather than a lifetime. Ruts matter for a reason that has nothing to do with comfort. A depression in a runway holds water. Standing water on a runway reduces the friction available to a decelerating aircraft, and, above a certain depth and speed, allows the tire to ride on a film of water instead of touching the surface. It rains very rarely in a desert city, which sounds like protection, but it is the opposite. Infrequent rain after a long dry spell lifts accumulated dust, rubber, and contaminants into a thin slick, and that first rain is the worst friction condition the surface will see all year. Rubber is its own problem. Every landing lays down a deposit of vaporized and abraded tire rubber in the touchdown zone, and rubber has very low friction when wet. Over thousands of movements, it builds into a dark polished band that covers the surface texture the pavement was built with and fills in the grooves that were cut into it to let water escape sideways. Removing it is a routine and expensive maintenance operation using high-pressure water or chemical treatment, and it has to be repeated on a cycle driven by traffic volume. Airport operators measure runway surface friction with instrumented vehicles and act on the readings, because friction is not a property you can see. Seeing any of this before it becomes a problem is its own discipline, because a pavement cannot be judged from the surface. The layer that fails is usually not the layer you can see. Engineers run falling weight deflectometer tests, dropping a known mass onto the surface and measuring how far the pavement deflects and how quickly it recovers, then working backwards from that deflection shape to estimate the stiffness of each buried layer. They cut cores and examine the asphalt in section, checking whether the binder has aged and hardened, whether the aggregate has begun to strip away from it, and at what depth the deformation actually sits. They walk condition surveys along the full length, recording cracking, rut depth, raveling, and joint condition, and reduce all of it to an index that can be trended from one year to the next. And they count movements, because the remaining life of a pavement is not measured in years, it is measured in load repetitions. Here, too, the measurements raise questions that are harder than the readings themselves. Do you test at night, when the pavement is cool and the results are comparable between surveys, or in the afternoon, when they represent the condition that actually matters? If rut depth has grown 2 millimeters in a year, is that the binder softening, or the base layer beneath it consolidating, or simply a heavier fleet mix than the design ever assumed? If 1/3 of the runway is measurably worse than the rest, do you resurface that third and accept a construction joint in the middle of a landing surface, or take the whole thing and lose the runway for twice as long? A pavement engineer is not answering whether the surface is good. They are answering how many more summers it has. So now put the two halves together, because the interesting part is that they push against each other. The air is thin, so the aircraft needs more runway. The pavement is hot, so the runway needs maintenance more often, and the maintenance takes the runway away. Resurfacing a runway is not a night job. It requires the surface to be closed for weeks, milled off, relayed and remarked. And at an airport with two parallel runways handling a very large volume of traffic, closing one of them removes roughly half the capacity for the duration. This is why major runway refurbishments at large Gulf airports are planned years in advance, announced to airlines far ahead, and deliberately scheduled outside the peak season. The engineering constraint and the commercial constraint are the same constraint. Then there is the third dimension that nobody in the cabin thinks about, which is what the heat does to the air above the surface rather than around the wing. A very hot pavement heats the air immediately above it, and that superheated layer rises in unstable plumes. The visible result is the shimmer that makes the far end of the runway appear to dissolve, and it degrades visual range along the surface. The invisible result is low-level thermal turbulence, and it arrives at exactly the phase of flight where the aircraft is slowest and closest to the ground. Which brings us to how any of this is actually managed, because it is managed every day with arithmetic. Before every departure, the crew calculate performance for that specific runway, that specific temperature, that specific pressure, that specific wind, and that specific aircraft configuration. They are solving for the maximum weight at which the aircraft can accept an engine failure at the worst possible moment during the takeoff roll and still either stop within the remaining runway or continue and climb away with the remaining engine at a legally required gradient. That single requirement, rather than the wing itself, is very often what sets the limit. If the answer comes out below the weight the aircraft is currently carrying, something has to leave the aircraft. Cargo comes off first, then fuel, which means a shorter range, which may mean a technical stop. Then, in the worst case, passengers. And every one of those calculations sits on top of operational questions that do not have clean answers. Which temperature do you use? The one reported now, or the one forecast for the moment you actually roll, after 40 minutes in a departure queue? Is the wind that is helping you going to still be there? If the intersection you were planning to depart from saves taxi time but costs you runway length, which limit binds first? If the pavement has been resurfaced on one runway and not the other, are the two surfaces offering the same friction? Has the surface temperature peaked, or is the worst hour still ahead? Every variable moves the maximum weight, and the maximum weight moves the commercial viability of the flight. The engineering solutions are as unglamorous as they always are. Build the runway longer than a temperate climate airport would need, so that the density-altitude penalty is absorbed by geometry rather than by payload. Specify a binder graded for the real pavement temperature rather than the air temperature. Groove the surface so water has somewhere to go. Build a parallel runway so that maintenance does not mean closure, and schedule the heaviest departures into the coolest hours, which is why a long-haul network out of a Gulf hub has such a pronounced nighttime departure bank. That bank is often described as a passenger convenience. It is also a performance decision. The choice between a flexible asphalt surface and a rigid concrete one is made area by area, and it is decided almost entirely by how long the load stands still. On a runway, an aircraft is moving quickly, and the load at any single point is applied and released in a fraction of a second, which is exactly the condition asphalt handles well. At a holding point, it is different. An aircraft may sit stationary at full weight with its brakes on for several minutes, in the hottest part of the afternoon, with jet efflux from the aircraft ahead of it washing across the surface. That is the worst possible loading case for a material whose stiffness depends on temperature and on time under load, and it is why holding points, apron stands, and taxiway intersections are so often built in rigid concrete instead. Concrete does not creep under a standing load the way hot asphalt does. It brings its own problems, because it expands and contracts with temperature and therefore has to be cast in slabs with joints, and those joints have to be sealed and resealed, and a slab that loses support beneath one corner will crack. But it does not slowly flow away underneath an aircraft that is waiting for a departure slot. When an engineer walks the same runway an aircraft has just landed on, they are reading a different object entirely. They see the dark polished band in the touchdown zone and read it as a friction measurement that is due this month rather than next. They see the faint parallel depressions along the center line and read them as a point on a trend line. They see the sealant in a concrete joint at a holding point and read it as the difference between water staying out of the base layer and water getting into it. The surface a passenger experiences as perfectly smooth is, to the people responsible for it, a set of readings all moving slowly in the same direction. What follows is a hypothetical engineering stress test. It is not a description or a prediction of an actual event at any specific airport. Imagine a severe combination arriving together. It is the hottest hour of the hottest week of the year, and the surface temperature of the asphalt is at the very top of the range its binder was specified for. One of the two parallel runways is closed for a planned resurfacing, so every movement is funneled onto the other. A dust event has reduced visibility along the surface, and the heat shimmer is severe. The wind has swung so that the departure direction now carries a light tailwind component, which lengthens every takeoff roll. A heavy long-haul departure is at the gate, loaded close to its structural maximum, and the departure queue is long enough that by the time the aircraft reaches the threshold, the temperature has risen above the figure the performance calculation was originally run at. Now the questions. Does the calculated maximum weight fall below the actual weight while the aircraft is already taxiing? And who notices first? If cargo has to come off, does the aircraft return to stand? And what does that do to a runway that is already the only one operating? Do the ruts along the main gear tracks hold enough of the morning's dust to change the friction the aircraft will need if it has to reject the takeoff? Does the tailwind component push the decision speed and the stopping distance into conflict? If an engine failed at the worst moment, is the climb gradient still available in air this thin? And if every one of these questions is answered correctly and the flight departs entirely normally, as it almost always does, what would anyone on board have seen? The answer is nothing at all. That is the point. The systems that resolve this are procedural rather than mechanical. Performance calculations rerun against actual conditions rather than planned ones. Publish temperature limits beyond which specific aircraft simply do not operate. Runway friction measured on a schedule and acted on. Pavement condition surveys that catch rutting while it is still measured in millimeters. Maintenance windows planned around a climate rather than around a calendar. None of these things make the air heavier. They make a thin air environment predictable, and predictable is the only thing that matters. A passenger walking through a Gulf hub sees the most controlled environment on Earth. Cooled marble, silent corridors, aircraft arriving and leaving on a rhythm that never appears to falter. They do not see that the air outside is doing everything it can to prevent it. They do not see a wing that needs more speed than it would need anywhere else, or an engine giving up thrust it would keep in a cooler place, or a surface that is quietly deforming a fraction of a millimeter under every heavy aircraft that rolls along it. They do not see a load sheet where the last few tons were removed because the arithmetic said so. The runway is the part of an airport that looks the most permanent and is in fact the most consumable. It is a machine surface with a service life, sitting in a climate that shortens it, carrying loads no road ever carries, in air that has to be worked much harder to fly in. Dubai did not build the world's busiest international airport by beating the desert. It built it by measuring exactly how much the desert takes, every single afternoon, and then paying that price on purpose. Aircraft performance, pavement design, and airport operations vary enormously by aircraft type, airline procedure, airport infrastructure, and local regulation. This documentary discusses general aeronautical and pavement engineering principles and does not claim that any specific airport, airline, or aircraft is operating unsafely or outside its approved limits. References to design and operational practice describe published standards and accepted engineering methods, not allegations of failure or non-compliance. The combined scenario described near the end is a hypothetical engineering illustration used to explain how several limits interact, and is not a report of an actual incident. Generic stock footage is illustrative and should not be interpreted as depicting specific aircraft, operators, or defects. This content is for educational analysis and does not replace professional aeronautical or civil engineering advice. If you want to understand the hidden engineering that keeps enormous cities and their infrastructure functioning, make sure to subscribe to the channel. Have you ever been on a flight that used far more runway than you expected? Tell us where it was, in the comments below.